If you had asked me to get you some sodium oxide, I would have no problem doing that because there is only one sodium oxide that exists. However, if you had asked me to get you some iron oxide, I would go to the shelf and I would see that there are two options for iron oxide. There's this black powder or there's this orange powder. So I would need a more specific name to know which iron oxide you actually wanted. So that's what this video is going to be about. What do you do in a situation where you have a metal like iron that has more than one possible charge? Iron can be a 2+ or it can be a 3+. So we're going to have a different naming system when we work with these metals. These metals with more than one possible charge we call type 2 metals. All right, so that's what this video is about. So type 1 elements, usually we're talking about metals. They only have one possible charge. Stuff like sodium can only become 1+ only. It only has one valence electron. Stuff like magnesium, calcium can only become 2+. All right, so if we're looking at a periodic table, that would be these elements. All right, but most of the metals on the periodic table can have more than one possible charge. So we'll be talking a lot about these transition elements in a D block, F block as well, and even some of the P block metals. They have more than one possible charge. Here's iron, the one we were talking about earlier, 2+ or 3+. So something like iron, it's a type 2 element. It can lose 2 electrons to become an iron 2+ cation, or it could have lost 3 electrons to become iron 3+ cation. All right, and just to kind of show how and why this can happen, I'm not going to do this for all 118 elements. That would be crazy. But using iron as an example, we can see its orbital diagram right here. I have it condensed. Iron is an element with 26 protons, 26 electrons. Its condensed orbital diagram. Past argon, we have 4s2, 3d6. All right, so iron could lose 2 electrons, like we said earlier. It would have been the 2 of the 4s electrons, and you would see an empty orbital here. You'd be left with those 3d electrons there. That'd be your 2+. However, iron can lose a 3rd electron, and it often does. It would be that 6th electron in the 3d orbitals, and that's easily done actually for iron because it removes this pairing energy, this repulsion between those 2 electrons stuck in the same orbital. And then so you would end up with an electron configuration like that. But the long story short here, we're not going to be doing tons of orbital diagrams. Iron has more than one possible choice. And so in the pictures we saw earlier, we saw iron as the black powder that has iron 2+ in it, and then we have iron 3+, which will form that reddish orangish powder. I thought I'd show you some samples of iron as found in nature. Iron only very rarely is found as the element. You usually find it in a mineral form, such as with sulfur or with oxygen. I did want to get a iron 2 oxide mineral in time for this video, but I wasn't able to find a sample. But this pyrite will have to do, also known as fool's gold. Okay, grows these beautiful cubic crystals. Right, if you're lucky to get a sample like that. All right, and in pyrite we have iron 2+, and then we have this polyatomic ion called a persulfide anion. All right, and they exist in a 1-to-1 relationship between the metal and the anion. Well, I guess you could say 2 sulfurs there because it's a persulfide. But yeah, that's iron 2+. All right, and then on the other side, we'll get to this one in a bit. We have hematite. All right, this is very chemically similar to rust. This is iron 3 oxide. Okay, nice red color here. Scratch, you can get red color on your paper. All right, and that has 2 iron 3 plus atoms, ions, for every 3 O2 minus oxide anions. All right, and then you have something like magnetite. This is my favorite one because it is magnetic. Here I have some water magnet toys. You can see it stick on. We're getting the metal wet. Or the mineral wet. With enough wetness and time, maybe it'll turn into that. And iron 2 plus is generally found in environments that are like more reducing conditions. You have a lot of like organics in the environment, and you with weathering, with more oxygen, can get more this stuff or this stuff in higher oxygen environments, more oxidizing environments. But yeah, magnetite's magnetic. Check this out. It features, this is interesting, 1 iron 2 plus and 2 iron 3 pluses. So 3 irons, but 2 different possible charges versus having 4 oxygens, all of the 2 minus charge. Okay. Not magnetic. The charge on the iron also has real-life implications for how much oxygen is stored in the mineral. If you have 100% pure iron, then, well, it's going to be 100% iron, no oxygen. For iron 2 oxide, again, I wish I had a sample of it, that's going to be 78% iron, 22% oxygen. On all these percentages are by mass. Got a label by units, all right? All right, and then we can see more increasing oxygen saturation in the mineral. If you have iron 2, 3 oxide, a mix of 2 plus and 3 plus, you're close to fully saturated in oxygen, but not quite yet. We have 72% iron and 28% oxygen. Full saturation of oxygen occurs when you have iron 3 oxide, like this hematite here. Iron's highest charge possible is 3 plus. So if you have all your irons as 3 plus, then you have 70% oxygen, or excuse me, 70% iron and 30% oxygen. So what other possible charges are out there? We talked about iron. I want to talk a bit about other metals. Again, we're not going to do every single metal. You don't have to necessarily take notes on this, but you know, we're in the transition metals here. Titanium is known for making 4 pluses. Scandium is known for making 3 pluses. And that's pretty much set in stone, but in the right conditions, you can actually change those charges. You know, something like vanadium is often found as 5 plus, but sometimes it can be found as like a 4 plus. Chromium, sometimes found as 3 plus, like in stainless steel, but the carcinogenic version of chromium is 6 plus. Manganese can be found as 3 plus, 4 plus, even 2 plus sometimes. I should have had that there. Even as high as 7 plus. I wonder if you're starting to notice a pattern. 1 plus, 2 plus, 3 plus, 4 plus, 5 plus, 6 plus, 7 plus. Ooh, is this going to be an 8 plus column? Nope. Iron can be found as 2 plus, 3 plus. Ruthenium, similar. If you're curious, osmium actually can go as high as an 8 plus. All right. Trivia question with osmium. It is the most dense element on the periodic table. All right. How about cobalt? Cobalt can go 2 plus or 3 plus. Nickel, usually 2 plus, but other possibilities are possible. Copper, usually 2 plus, but sometimes a 1 plus. Zinc is, actually, it's always a 2 plus. The Z kind of looks like a 2, right? Same can be said with cadmium. But yeah, there's all sorts of nuance to these things sometimes. Some chemists, they'll see a charge being told that it's impossible, and they'll try to make that charge possible. But yeah, oh yeah, I can't forget my favorite. Uranium, usually found as a 6 plus, but it can be found as a 4 plus in nature as well, and people have even made 2 plus, 3 plus, and 5 plus. with it. Who knows? Maybe there's a 1+ out there. But just kind of as a summary, here's the list of my favorite type 2 metals. And I wrote the possible plus charges out here in purple. The two I test on the most often would be iron, being a 2+ or 3+, and lead as a 2+ or 4+. Occasionally, if I'm not like pressed for time in a semester, I might throw like copper and uranium on those tests. But iron and lead, these two affect so many fields of study out there. I like to study on those too. But yeah, if you want to learn more about possible charges, the ptable.com has a nice reference. Here it is. So normally when you open ptable.com, it gives you the standard periodic table, but you can play with these other features too. This isotopes feature, I wish I had that the other day, but electrons, right? You can see the variety of charge states, like iron can be a 2+ or 3+. Let's see, uranium can be a 4+, 6+. It only says 6+ there, but yeah, you can play around with this, and heck, you can even click like the compounds thing, and you can click iron, click oxygen, and then it can show you all sorts of different chemical formulas involved. Just kind of just test your knowledge and understanding, so feel free to play with that. All right, on to the main point of the video, which is showing you the template for how to write names when you have a type 2 cation. It is the same as in my previous video with ionic compounds, exactly the same, except if you have a type 2 cation, you simply have to show that charge in Roman numerals. If you have a monoatomic ion, everything in my video today will be monoatomic. It's going to be ending in "ide." We'll talk about polyatomics in the next video. All right, so let's go on to some examples. We'll do like we've always done, some formula to name examples, then going the other way, name the formula, and then we'll end with some what's wrong examples. All right, so first up, we got FeO. So we have to figure out what charges are here. All right, so let's see. So when I see an ionic compound with a metal with more than one charge possibility, I always go look at the anion first. Okay. Look at the, oh my gosh, I wrote that upside down. But look at the anion first. All right. And so oxygen, thankfully, is one of those elements that always has a constant charge. And when that charge always is for oxygen is a 2-. And ionic compounds have to be net zero. They have to have a net zero charge. So I ask myself the question, what must the charge be on iron to make this neutral? And it must be a 2+. 2 and -2 equals 0. And so now I'm ready to write this name. I can go write iron. I see it has a 2+ charge, so I'm going to write 2 in Roman numerals. Close the parentheses. My understanding is most people do not want a space right there. Now we're going to have a space here, and then we just write oxide. That's the name of the anion. So iron 2 oxide for FeO. Okay. Let's put you, oh, sorry, I was off the screen. Let's put you in a teacher's seat for a moment. What would you guess would be the most common incorrect answer for FeO? Maybe you thought of this. Maybe someone was correct in thinking about parentheses, but they were counting the atoms instead of looking at the charge. So remember, parentheses is charge. It is not a count. All right, let's go to Fe2O3 next. So we have 3 of the O2 minuses. And then we have 2 of the irons. We have a total of 6 minus here, which means this side with the pluses must be a 6 plus. All right, so we need to figure out what number needs to go on each of these to get it to 0. Well, okay, we already figured that out, but we have to figure out how to distribute it to these two. So 6 plus divided by 2 equals 3 plus each. Okay, we have 2 iron atoms. 6 plus divided by 2 iron atoms, 3 plus per iron. So that gets us to a 6 plus, and that will neutralize the 6 minus. Since we have a 3 plus, we will then say iron 3 oxide. Okay? Putting you in the teacher's seat for a moment. This is iron 2 oxide is the most common wrong answer for this. Again, people will start counting that subscript instead of thinking about the charge. All right, let's get these two done. UO2, we have a 2 oxide, so that's going to be a total of 4 minus, which means this uranium must be a 4 plus. So this would be uranium 4 oxide. Okay. And there's a mineral name for that, but I think I've done enough geology today, as much as I love geology. And then UO3, we got 3 of them, so that means it's going to have to be a U6 plus. So this is going to be uranium 6 oxide. All right, let's go to our next set of examples. We're going to go from names to formulas. All right, so the nice thing about going from names to formulas when you have type 2 metals is when you have a type 2 metal, you're forced to tell someone what the charge is on the metal. So that means you are told what the charge is on that copper. It's a 1 plus. Chloride is always a 1 minus. It's in group 17. The halogens, everything here is always a 1 minus. All right, so we only need 1 of each, so we get CuCl. Copper 2, chloride. We need 2 chlorides to neutralize that copper, so we're going to get CuCl2. All right, copper 1 sulfide, Cu plus, S2 minus, oxygen, sulfur is in the same group as oxygen, the 2 minus column. Sorry, allergies, man. Cu plus, S2 minus. So we're going to get Cu2S. Okay. If you still like doing crossover method, you're more than welcome to do that. Okay, which is the same as that. We just don't write the 1. Cu2 plus, S2 minus for copper 2 sulfide. We only need 1 of each. So we get CuS. All right, so different name means different formula. Last slide. Okay, I love doing these. What's wrong? Why can't we simply just say lead oxide? That's because lead is one of those metals that can be a 2 plus or a 4 plus. So that means there's 2 possible lead oxides that could exist. All right. How about this next example? Let's say I'm putting you in a teacher's seat again, and someone wrote this. What sort of commentary would you give to someone who wrote something like this? To me, it looks like they took the subscript and just put it into the parentheses. Again, like I said earlier, that's the most common error. Let's figure out what's really going on here. Oxygen is always a 2-, which means this copper must be a 2+. So this should be that, because that goes there. And then here, oxygen is a 2-, which means we have 2 coppers. They're going to be a 1+ each. That'll give us a total of 2+, just 1 on each. So we take that, put it there, and that should be just a Roman numeral of a 1. Okay. All right, last one, dimanganese heptoxide. They probably mean 2 manganese and 7 oxygens. But manganese, once again, like every metal today in this video, is a type 2 metal, which means we have to say what the charge is. So let's figure out that charge. We have 7 of the O2 minuses. 7 times 2 minus is going to be 14 minus. We have 2 manganeses, manganese atoms, ions. And we need it to be a 14+ total, which means we need to distribute that 14+ over the 2 atoms, which means 14 divided by 2, that's going to be a 7+ each. So we would write manganese 7 oxide. That would be the correct name. Manganese is a really interesting element. I saw some recent news about these manganese nodules sitting at the bottom of the ocean, and they can be used to, they generate this dark oxygen, oxygen without photosynthesis. There's like electrochemistry going on at the bottom of ocean beds, driven by these manganese nodules. This is not a manganese nodule. Manganese nodules have like elemental metallic manganese in them. All right, so hopefully this helps. Long story short, if you have a type 2 metal, you must use parentheses. If you don't have a type 2 metal, don't use parentheses. That's still the common practice today. Type 1 metals do not use parentheses. Something like sodium, calcium, aluminum, things like that. All right. Hope this helps. Take care.